I'm going to record the rest of it so that anything else we say that's useful, I can just post on my courses for other people to see. All right, what do y'all want to look at next?
Can we actually talk about number 1 from chapter 6? Because, right, number 1 is one of them that we'll be testing.
Right. Oh, yeah. So grading number 1 for chapter 6, there was people seem to have some trouble with describing where the condition numbers are large. But the basic idea there is, I mean, in general, people did fine on writing down what those condition numbers were, like the C of x and the kappa of x. Because there you just need to be able to find the derivative of the function. And then maybe do some simplifying. But the main thing you're looking for when you're describing where the condition number is large, I mean, just think about how those functions behave. If they have any vertical asymptotes, then that's going to be a trouble spot. If they get bigger as x gets bigger, then that's where you'd have trouble. So let's just maybe pick a few of those and try them. Let me go back to the whiteboard. All right, so well, first, if anyone's watching this recording that's not here for the review session, what's on the board right now is we were just talking about number, what number was that?
14.
14 in chapter 7. And it's all about figuring out what your matrix A and your vector B should look like. So maybe, I don't know, hopefully this would help a little bit if you're able to see this. But so let's just pick a few of these functions. Let's say, like, for example, y equals natural log of x. So if we're doing condition numbers, what's the definition of our absolute condition number, c of x?
It's the absolute value of f prime of x.
And then what's the definition for our relative condition number?
It's like absolute value of x times f prime of x divided by f of x.
Okay. So here in this case, y prime obviously is 1 over x. And I mean, I guess the domain for the natural log function to begin with is x bigger than 0, right? And the reason I say that is because our condition number here is technically absolute value 1 over x. But I guess technically if we're starting out with positive x values from the beginning, then this is always going to be positive. So in this case, maybe it would be okay to write this without the absolute value bars. But on the homework, I was seeing a lot of people write their answers without absolute values in places where you really have to have the absolute values. So be careful with that on the test. In general, I mean, the safe thing to do is to just leave the absolute value around your condition numbers. But if this absolute value 1 over x gives me my absolute condition number, when is this large?
When x is really small.
Okay, yeah, when x is close to 0. Right, because then you're close to dividing by 0. So then you're close to infinity. All right, so that's one of the main ideas in most of these is if it's a fraction, see if there's something that makes the denominator 0. If it makes the denominator 0, then you've got trouble. The relative condition number, here we would have x times 1 over x divided by the function itself, which is natural log of x. So you're left with just 1 over natural log of x. And here again, in this case, natural log sometimes is positive, sometimes it's negative. So this absolute value does make a difference here. These condition numbers, by definition, always have to be positive. And so if you're missing the absolute values here, then the answer is wrong. So here again, if I want to say when the relative condition number is large, what would make this be a big number?
For the bottom to be a small number, close to 0.
Yeah, so if this is large whenever natural log is x is close to 0, right? But we can be even more specific, right? When is natural log of x close to 0?
When x is close to 1.
Right, so this means our relative condition number is large whenever x is close to 1, because natural log of 1 is 0. So the main idea on this type of question is to write down these functions that describe your condition number for different x values, and just figure out what makes them big. And so the main thing you're looking for are things like vertical asymptotes or maybe end behavior. And Yao, you're asking close to 0, or is there a difference between 0 from the left and 0 from the right? Yeah, was that a question for the relative condition number or the absolute condition number? Or both? Relative? So for the relative, you're asking about this part, natural log of x close to 0. So natural log of x is close to being close to 0. It can get close to 0 from the left or the right. I mean, I guess if we wanted to be a little bit more specific, the natural log, we know what the natural log function looks like, right? And right around 1 is when it's close to 0. So maybe if we're coming in from the left, then then you'd be doing 1 divided by a negative number that's close to 0. Coming from the right, you'd be doing 1 divided by a positive number that's close to 0. But then in the end, if we're taking the absolute values, then that's not really going to make a difference. So yeah, I don't think we have to specify from the left or right here. We just need to say that if x is close to 1, then the condition number will be large. All right, so that was for the natural log function. Did y'all want to pick another one of those to look at?
Which one do you want to do, Monty?
I mean, that was helpful just to be able to like explain it better. That means I'm good.
One thing I'll mention on part F.
Yeah, that one was rude.
Let me just write down. So on part F, the function was arc sine of x. And your derivative is the 1 over the square root of 1 minus x squared. And so something that'll help a little bit with talking about this one is the domain of the arcsine function, the sine function. The y values are stuck between -1 and 1. For your arcsine function, the x values are stuck between -1 and 1. So here, our domain to begin with is values between -1 and 1. Okay. But we can include 1 and we can include -1. So first off, for the absolute condition number, we've got absolute value 1 over the square root 1 minus x squared. And again, the main idea here is what makes this large. And if it's a fraction, one of the main things you're going to look for is something that can make the denominator 0. So when is the absolute condition number large?
X is equal to 1.
And when else?
And as it gets closer to -1 also.
Yeah, so
Yeah.
at 1 and -1, you have trouble. And it's not just at 1 and at -1, it's when you're close to 1 or close to -1. Because if x is close to 1 or -1, then the denominator is close to 0. If the denominator is close to 0, then that's a big number. So when x is near 1 or -1. Okay. And for the relative condition number, this one was a little bit uglier, but this comes out to x over arc sine of x times the square root of 1 minus x squared. Inside the absolute values. And so here, Again, because of this piece in the denominator, if x is close to 1 or -1, then you're going to have trouble, right? So you could kind of take the same thing and say it over here too for the relative condition number. The thing that some people didn't talk about that I would have liked to see is there's something else that could give you a 0 in the denominator. When is arc sine of x equal to 0?
Oh. At 0.
Mm-hmm.
Okay.
So this is something you have to address because anything that makes the denominator 0 could give you trouble. Okay? And so we need to see what happens here when x is 0, because if x is 0, then you've got 0 in the denominator, and you might have a large relative condition number. But if I do, if I look at how this behaves when x is near 0, well, then I've got 0 on top and 0 on bottom. That's an indeterminate form. If it's an indeterminate form, then we can't tell by looking at how it's behaving. Okay? So how do I figure out how this thing behaves as x approaches 0?
L'Hôpital.
L'Hôpital, yeah. Yeah, so if I want to see what's happening here, I want to evaluate this function at 0 or near 0. I can do this limit, but if I just plug in 0 as it is, I'm going to get 0 over 0. That's an indeterminate form. So we need L'Hôpital's rule. So we do the limit as x goes to 0. And I'll just write this down. The derivative of the top is obviously 1. The derivative of the bottom, you'll have to do the product rule, but what it comes out to is 1 minus x times arc sine x divided by the square root 1 minus x squared. Okay, you can do that derivative on your own and double check that, but I believe that's what it comes out to when you do the product rule on bottom. And now as x goes to 0, this will tell us if we actually have trouble near 0 or not. As x goes to 0, I've got 1 divided by 1 minus 0 over 1, which is
Dr.
just,
Graham, I don't think we can see that.
oh, you can't see that? What if you maximize the whiteboard window?
Marty, can you see it? And I can't see things.
I mean, yeah, I can see it.
Here. There, I moved it up to the top.
I appreciate it.
So, but in the end, after we do all this work, it turns out that when x is near 0, even though we would have 0 in the denominator, things kind of balance out with the numerator, and as x approaches 0, the y values are approaching 1, or the relative condition numbers are approaching 1, so that's not a problem. But I go through all that just to kind of emphasize the idea that anytime you have 0 in the denominator, you have to take a little bit of time to evaluate what's happening there. Is it a vertical asymptote that's giving you trouble, or is it behaving nicely there? Does that make sense?
Yes, sir.
All right, so that's probably good for number 1, right? Do y'all need to look at any more of those?
I don't think so.
No.
Okay, what else do I want to look at?
I actually don't think I have any more questions about like the test stuff. So.
Okay.
Um,
Uriel?
nothing on my part. Chapter 7.
All right, y'all, what do you want
All
to
of
look
it.
at? Yeah, number 15 will not be on the test. And that one, it sounds, I know that number 15 seems confusing when you read it, but I think in practice, it's not as hard as it sounds. Like for part B, part A is just a little bit of algebra. Part B, I think it's just a matter of changing the MATLAB code where they have the H values put in the square root of H values, and then everything else should be the same.
I was like, Daniel and I were working on this yesterday, and we were like, what does this mean? And then we're just like, you know what? This is what we're going to go with. Square root of H everything.
Yeah. Yeah. So the idea is that if you try to come up with a line that fits the height versus the distance, you get that line, but there's some error there. And you could decrease the error because it turns out that the distance is proportional not to height, but to the square root of height. So if you just take the square root of the H values and then use that in your code instead of the H values, then it should give you a better answer. But yeah, that one's not going to be on the test. I think it wouldn't be too bad once you have it figured out. But as far as testing the main ideas from the chapter, I think number 14 is a better test of that than number 15 is. All right. Any other questions?
No, sir.
Mari, do you want to look at a little bit more at number 6 just for the fun of it, or do you want to?
Just for the fun of it, the pure fun of it, yes.
There's no sarcasm there at all?
Not an ounce.
So solving an upper triangular system, u times x equals y. So let me explain it a little bit differently from how we talked about it yesterday. Let me actually just write out a few lines of work. Okay, so let's see. And what I'm going to write here is I'm going to go back to what they did with the lower triangular matrix. Let's see, what page is that on? Chapter 7 is long.
Yes, it is.
Oh, there it is. 120. So, like we were talking about yesterday, it's basically the same as what they did with the lower triangular matrix. You just have that extra step of division, right? But we can kind of explain this without using all the sigma notation. Let's just think about what it would look like to solve one of these things. Oh, I don't want red. Go back to black. So if it's upper triangular, you've got entries along the diagonal and zeros all below it. And then you've got your B vectors over here, or your B entries over here. B1. All right, so if I hand this matrix to a linear algebra student and say, what's the first thing you can do here to start solving? What would be the first step?
I would like divide by the use, is that a u, or yeah, u sub n to make that a 1.
Okay, yeah, so divide, so you would do, and that would give you your nth y value, right? If you're solving, or x value, if you're solving u times x equals b, then your nth x value would be just b sub n divided by u sub n, right? And then you'd go up to that line above and you'd do some back substitution and solve. And so you'd have, let's see, this is the n minus 1, n entry. So now what we would do next is we would use, let's pretend like we turned this into a 1. And if you're doing like row reduction, what would be your next step?
I would make the one above it a 0 and then divide by the number next to it.
Right. So we would first we would replace this row with so this I'll just call this row n minus 1. minus whatever that entry is. Um, oh, here, I think that this is not the best way to write it. Let me write this in terms of this, what this would look like in an equation. I would have, I really liked the L version better in the book because my indexes weren't as ugly. Here, let me write this a different way. I'm going to do this in terms of I'm going to do the L version like they do on page 140, just because the indexes aren't as ugly, and it gets the same idea across.
Can y'all hear that?
No.
Let's see.
Okay. So this is like a LU or LX equals B instead of UX equals B with lower triangular. But it's the exact same idea as an upper triangular. We don't have to do a whole bunch of n-1 indexes and n-2 indexes and stuff like that. So it's cleaner. But same idea. If it's upper triangular, we would start. If I go across that first row, I have that L11 times X1 equals B1. Right? Just doing this matrix L times this vector X. That first row being multiplied by X would give me this equation. So then X1 equals B1 divided by L11. Okay. For the second row, let's look at the equation that this gives us, because I think this makes more sense than talking about the row reduction. If I do this product, the second row times X, the equation that would give me is L21 times X1 plus L22 times X2 equals B2. Does that make sense? No.
Mm.
So do I'm doing this second row multiplied by x, but after the L22, those are all zeros. So technically you have plus 0 times x3 plus 0 times x4.
Oh, okay.
Write down
And
all.
just cancel everything out. That makes sense.
So now if I want to solve for x2, let's think about what I have to do here. I would subtract off the L21 x1. And then I divide off the L22. This is basically the same as describing the process for row reduction, just doing it, writing out a slightly different way. So to find x1,
Wait, are we supposed to, is that supposed to be divided by?
divided. So the big idea here is we're trying to figure out the number of operations. To find x1, we did one operation, a division. To find x2, we had to do a multiplication and one multiplication, one subtraction, and a division. Okay. Hold on, I think someone else.
Just trying to join.
Should be Mariah, yeah.
Oh, Mariah. Hey, Mariah.
Hi.
Howdy.
How's it going?
Nothing much. Just had breakfast. Sorry I'm late.
That's fine. So actually what we're talking about right now is a homework question that's not even so I don't know how useful that is, but we've kind of already gone through all the test questions that everyone had. But maybe after we finish this, we can look at whatever, maybe another test question that you have, Mariah.
Okay, I sent you an email yesterday. It was like late last night, so I don't know if you like got it or not.
Yeah, I think you're asking about how to explain your answers for number 1 in chapter 6.
Yeah, like I know how to find the condition numbers, but I guess the explaining like what they meant was a bit confusing.
Yeah, and we talked about that a little bit earlier. And actually, I think I'm recording all of this.
Okay.
So, I mean, we could kind of summarize it a little bit, but if you want to go back to the recording, I'll post the recording, and then you can look at that part, and maybe it'll explain it a little more.
Yeah, that'll be fine.
I think, yeah, this is the page we were on. So the main idea is once you find your condition numbers, so like if my absolute condition number is 1 over the square root of 1 minus x squared, you want to think about, well, what makes that function big? What x values make that big? Well, that's big whenever x is near plus or minus 1, because then you'd have a 0 in the denominator. If you have a 0 in the denominator, then you have a vertical asymptote, which would give you large answers. Same thing for the relative condition number. If x is plus or minus 1, then you'd have a 0 in the denominator. And so you still have the same problem for your relative condition number when x is near plus or minus 1. But then we talked a little bit about this arc sign in the denominator. That can be 0 if x is 0. So then, again, if there's something that makes the denominator 0, you need to think about what's happening there. And that's where we did all this work up at the top to figure out what's happening when x is close to 0 for our relative condition number. You get 0 over 0, which is indeterminate, so we did L'Hopital's rule, and we got 1, which tells us at 0, even though you get 0 in the denominator, it's not a problem because it's getting close to 1.
Mm.
And so there's not another vertical asymptote there. But I mean, the main idea for the explanation there is just look at the function and find what x values make these functions big. And the main thing, in most cases, that's just a matter of asking, you know, where would you have vertical asymptotes? Or what would make the denominator 0? There could be other things you look at, like on part E, where you have the exponential function. That gets big as x gets big. So that could be part of your answer too. You could look at what happens as x goes to infinity. But play that, we did a couple of examples of that. So you can play that back when I post the recording if you want to see more about it.
Okay, thank you.
Mm-hmm. Okay, so just to finish this question real quick, let me write down one more of these computations. If I'm doing L times X, then let's look at the third row for a second. I don't have it written down, but what it would look like is you'd have L31 times X1 plus L32 times X2 plus L33 times X3, and then plus a whole bunch of zeros times all the other x's. So you don't have to write those down. And that should equal the third entry in your B vector, so that would be B3. So then if I'm going to solve this, I need to, if I'm going to solve this for x3, I would subtract off the other two terms. So minus L31 x1 minus L32 x2. And then after I subtract all those off, I would divide the L33 off. Okay, so to find x3, I had 2 subtractions, 2 multiplications, and then 1 division. Okay, and you can kind of pick up on the pattern on what it's going to take here. For x in general, for xi, you're going to need I minus 1 multiplications. You're going to need I minus 1 subtractions. And you're going to need 1 division. So the total number of operations it takes to find xi, what that totals out to is 2 times I minus 1 plus 1. That's the total number of operations to find xi. We need to do x1, x2, x3, all the way to xn. So for your total operation count, you're adding all these up. The sum of your operation counts from I equals 1 to n of this 2 times I minus 1 plus 1 gives you your total number of operation counts. So, Mari, I don't know if kind of writing out these lines helps in any way. But maybe if you write out one or two more of those lines and kind of pick up on the pattern, you'd start to see how many operations it takes to do each one of these. And then you want to add up the number of operations for each one. Mari, does that help at all?
I mean, yeah, like that process makes sense to me.
Mm-hmm.
Yeah.
So basically what I'm saying is, if you're worried about understanding where the double sum came from at the top of page 141, basically what I'm saying is we don't need to write that double sum. We just kind of think about, we're kind of skipping to the next line in that and just thinking about this single sum here. I did that with my mouse instead of my stylus, so that looks terrible. If you have MATLAB code that you're looking at, it's kind of easy to see what's happening in each step. But here I'm just trying to answer it without looking at any MATLAB code. But again, Mariah, I said this at the beginning. If you go up to the top of the chat, the questions to focus on for chapter 7 are numbers 1 and 4, and then 8 and 9, and then 14. So this whole operation count thing is just kind of bonus. It's not even part of the test.
Okay.
So maybe there's time for one more question. Mariah, did you want to ask about something else?
Let me see. You said 1, 4, 8, 9, and 14, right?
Yeah.
Right now, I don't think I have any, but I'll probably look at your recording and see if I still have questions. I'll probably email you and stuff.
Okay. I feel like there was another question you had in your email other than about that first.
Because I had a typo in number 2 in chapter 6, so I didn't know I had the process right. Because I know that the numbers would be off because it was the wrong formula, but I didn't know I had like the actual process right of number 2 for number 6.
Oh, right. Yeah, let's look at 2C for a little bit just to finish out because I think that gave some people trouble. All right, so our absolute condition number is just the absolute value of the derivative. So 1/3 x to the negative 2/3. And again, make sure you have the absolute values here. For this function, x, since it's a cube root, x can be positive or negative. So whether or not you have the absolute values makes a difference in your answer. So that's our absolute condition number. The relative condition number just came out to be 1/3, right? But that doesn't really play a role in part C. So what they say in part C is suppose x was originally 10 to the negative 17th, but then maybe due to round off error or whatever the reason is, the computer maybe interprets it as 10 to the negative 16th. All right, so that seems like a pretty small change. Relatively, might be a big change, but I mean, going from 10 to the negative 17th to 10 to the negative 16th doesn't seem like that big of a deal. So use the absolute condition number of f. Oh, I think I may have been saying this backwards. Right. Oh yeah, the absolute condition number. I was getting mixed up for a second. The absolute condition number of f was c of x. Okay, so using the absolute condition number of f, how much of a change is expected in our function due to this small change in the argument? So in other words, how much do our y values change here? We should expect our y values to be roughly equal to our condition number times the, so the change in the y values should be roughly equal to the condition number times the change in the x values. All right, so how much of a change is expected in our y values? Well, in this case, our condition number, what is our condition number for 10 to the negative 17th? It's 1/3 times 10 to the negative 17th to the negative 2/3. So it's 1/3, 10 to the, I don't know, 34 thirds, whatever that is. So this is 1/3, 10 to the 34 thirds times the change in our x values. And our change in our x values was from 10 to the negative 17th to 10 to the negative 16th. I guess to get rid of the absolute values, let me switch the order of subtraction because 10 to the negative 16th is a bit bigger number. So basically, to answer that part C to this question, how much do your y values change, or how much change should you expect in your y values? Whatever this simplifies to would be the answer to that. So you would distribute this 10 to the 34 over 3 into the parentheses and multiply it by 1/3. And whatever that comes out to would be your rough estimate how much your y values change. I don't have a calculator with me, so I don't know what that looks like, but
I got something like 6.4633 times 10 to the negative 6.
6.4
33.
33 times 10 to the negative 6.
times 10 to the negative 6.
And there should be a 6 between the 4 and the 3s. Yeah.
Okay. So the thing that's important about this, or the thing that I want you to understand, I mean, this is just kind of some computation, plugging some numbers in, but notice how big of a difference this is from how much the x values changed, right? There was very little change to my x values from 10 to the negative 17th to 10 to the negative 16th. That's a really small change. Compared to that small of a change, this is a pretty big change, 10 to the negative 6th. Is pretty significant. So even though we had a really small change in our x values, our change in y values was much larger. I mean, we still think of 10 to the negative 6 as being a small number, but compared to how much your x values change, that's a pretty big difference. Does that make sense? So yeah, that's basically how the computation would look for part C. It's really just using this definition of the absolute condition number and plugging in the x values that we're working with. So I don't remember how that looked on your homework or how you did it, but does that help, or does that make sense?
Yeah, I did the same thing. It's just that my numbers are off because I had my condition number was off, but it was roughly on the same process.
Okay. All right. I think we're about out of time for now. But I mean, I guess I have my regular office hours this afternoon still, 1 to 5. So if you come up with more questions, you're welcome to come back. I have one calculus student that has been showing up pretty regularly to office hours, and so she may be on if you come by, but we can just kind of, I don't know, if you need to ask questions, y'all can take turns or something. So other than that, I'll post this recording so other people can watch it that weren't able to come, and let me know if you have other questions.
Thanks, Dr. Graham.
Thanks, Dr. Graham.
Welcome.
Bye.
Bye. It's good to see you all.
Good to see you too.
Good to see you.